Okay, we are recording now. So hopefully you guys are able to see the slides that I am sharing with you. Let's get started. Today we are going to be talking about similar matrices. So what is, if two matrices are similar, then what are the conditions? Can we transform a matrix into a diagonal matrix? Can we, are all matrices diagonalizable? Which essentially means that you only have elements in the diagonal, all the other elements of diagonal elements are zero. So we'll talk about why those kind of matrices, why diagonal matrices are good to work with, mathematically convenient to work with, and we'll look at those transformations. So this is from the textbook section 4.7. So before we talk about what makes two matrices similar, let us work through a diagonalization example. So we'll take take A as a 2 by 2 matrix, right? So this guy is a square 2 by 2 matrix, and we have actually worked with this particular matrix in the previous class where we found its eigenvalues and we found its eigenvectors. So when you work with this particular matrix A, you get two eigenvectors, x and y. These are your two eigenvectors that correspond to two eigenvalues. So if you look at the characteristic equation, find determinant of a minus ti, set it to 0, you get a characteristic polynomial. The roots of that characteristic polynomial work out to be 2 and I believe -1. Yes, 2 and -1. And if you look at what is going to be the eigenvector that corresponds to lambda equals 2, which essentially means you are looking for a minus 2i x equals 0. So you're looking for the null space of a minus 2x and a plus x, a plus I times x equals 0. So if you look at those eigenvectors, you will see that those eigenvectors work out to be 2, 1 and 1, 2. These are your two eigenvectors. We have already seen, we have actually derived these vectors before. So if I take the matrix and the two eigenvectors, I can construct a square matrix S. So I'm trying to construct a square matrix S, whose columns are the eigenvectors of the matrix A. So I have two eigenvectors over here. I'm highlighting them in blue, x and y. I'm just going to make these guys columns of my S square matrix. So if I put them as two columns right here and right here, I get two columns for S. Now I have a square matrix S, which essentially contains the two eigenvectors. Those eigenvectors actually correspond to this matrix A. Now I'll also find S inverse. So S inverse can be quickly found by doing 1 over the determinant of S and then switching the diagonal elements, negating the off diagonal elements. Because there's a 2 by 2 case, it is pretty easy to find out S inverse. So I have S inverse, and I'm trying to diagonalize this matrix A. So what I'm going to look at is the product S inverse multiplied by A multiplied by S. So what I'm doing over here is taking that original square matrix A, I am post multiplying it with S, and I'm pre-multiplying it with S inverse. So I've got the S inverse right here. S inverse is right here. And I've got my A matrix plugged in the middle, and I've got the S matrix all the way to the end. Now, if I multiply it out, these are all 2 by 2 matrices, so the sizes satisfy and you will be able to carry out that matrix multiplication. The end result is going to be a diagonal matrix. So I can use, say, D for this, and I can say this equals D. So what I have is elements in the diagonal, but all the off diagonal elements are 0. So that's what we call a diagonal matrix. So here in this particular example, S, this square matrix which consists of eigenvectors, is actually diagonalizing A. So I took A, which was not a diagonal matrix, and I transformed it into a diagonal matrix, and I used S, my square matrix, with eigenvectors to do that. So I've essentially transformed a square matrix into a diagonal matrix. Now we are ready to look at the definition of similarity. Now, two matrices A and B are considered to be similar if this particular condition holds true, which essentially means that there is some matrix S that you can use with A to get B. So two matrices A and B are similar. A and B are similar if you take A, post multiply it with S, pre-multiply it with S inverse, and you get B. And if there is such an S that exists, then you consider A and B to be similar to each other. So what is good about being similar is if two matrices are similar, then they have the exact same characteristic polynomial, which also means that they have the same eigenvalues. Not true for eigenvectors. Their eigenvectors are not the same, but if two matrices are similar, then we can say that they are going to have the same characteristic polynomial, which means that determinant of A minus Ti and determinant of B minus Ti is going to exactly be the same, and we'll prove it. And if the characteristic polynomial is the same, you set it to 0, you are going to get the same eigenvalues. Let's try to prove that if two matrices are similar, then they will have the same characteristic polynomial. So to do this, we are considering the determinant of this particular matrix here. So what is this? This is to get the characteristic equation. What do? We say we evaluate the determinant of that matrix B minus Ti and set it to 0, right? So let's try to evaluate B minus Ti, where for B, I'm essentially substituting S inverse AS, because that condition has to hold true if two matrices are similar. So if I look at this determinant of S inverse AS minus Ti, for I can substitute S inverse multiplied by S. So right here, I'm substituting for I, I'm substituting S inverse S. Next, because matrix multiplication, I can distribute it. I'm taking S inverse from here and here, and I'm taking S, putting it at the end. And what I'm left with is A minus Ti. So imagine that there is an I in there, S inverse IS. So that Ti is going over there. So whatever is left over. Now, if you look at this, determinant of S inverse multiplied by A minus Ti multiplied by S, we know the property of determinants. So when you have determinant of A times B, it will be the same as determinant of A times determinant of B. So you can break this down into three different products of determinants. Determinant of S inverse, determinant of A minus Ti, and determinant of S. So this is essentially due to the property that determinant of AB equals determinant of A multiplied by determinant of B. That's what we are using first. And then if you look at this, you have determinant of S inverse over here and determinant of S over here. And we also know the property of determinants, that determinant of S inverse is simply 1 over determinant of S. So by using that, this guy is going to cancel out with this. What you're left with is essentially determinant of A minus Ti. So what we proved over here is determinant of B minus Ti equals determinant of A minus Ti, which means that the characteristic polynomial for A and B is going to be exactly the same, right? We proved this. And if we set that to 0 to find the eigenvalues, because the same characteristic polynomial, we are going to end up with the same eigenvalues. So here we are saying if two matrices are similar, we are going to have the same eigenvalues, and that is really because of same characteristic polynomial for those two matrices. The reverse is not true, however, and we'll take a look at that as well. So if you have two matrices with the same eigenvalues, that does not imply that they are similar. And to prove this, we are taking a look at these two matrices, A and B, A equals 2032. It's a 2 by 2 matrix. B is 2 times I. Literally in the diagonal it has elements 2. Now if you look at the characteristic polynomial for A and B, because their diagonal elements are exactly the same, when you do determinant of A minus Ti, you are going to A minus Ti or determinant of B minus Ti, you will see that both these characteristic polynomials work out to be 2 minus T squared. So the characteristic polynomial for these two matrices are exactly the same, 2 minus T whole squared. The eigenvalue is 2 and there are 2 of them. So the algebraic multiplicity for eigenvalue 2 is 2. But we will see that these are not similar. So this is the case where the characteristic polynomial is the same, but these are not similar matrices. And we can prove that by assuming that in fact there is a matrix S that is invertible that satisfies this criteria. So we are assuming that they are similar, and then we are by contradiction we are going to prove that they are by contradiction we are going to prove that they are not similar. So the way we do that is assuming that they are similar. Let's assume that they are similar. And if I take this particular condition here, S inverse AS equals B, let me write this down over here. S inverse AS equals B. What I can do is I can multiply over here with S inverse, which means I have to multiply here by S inverse. And I can also, let's see, I'll take black. I can multiply over here with S, which means I multiply here with S. Now, if I do this, you see what happens. All of this becomes identity. All of this becomes identity. And you're left with A equals S B S inverse. So if that condition were to be true, if the matrices are similar, another way of writing that is A equals S B S inverse. Now, what is B? We know that our B that we are using is simply 2 times the identity matrix. So we can substitute for that. So we got S B S inverse as 2 S I S inverse. So essentially B equals 2I is what we are substituting over here. Right? B equals 2I goes over there. And then the identity matrix, I can remove it from my multiplication. So I'm left with 2S times S inverse. S times S inverse is simply going to be I, and 2 remains as is. So what did we get? We got A equals 2I. And you clearly know that A is not equal to 2I. There is a 3 over here, which is breaking that equality. That breaks this. That's a contradiction. So what we can say is that there is no S that exists that will satisfy this particular criteria, also proving that A and B are not similar. So here we have a case where the eigenvalues in the characteristic polynomial are exactly the same, however, they are not similar. So same eigenvalues does not imply similar. However, if they are similar, they have the same eigenvalues and the same characteristic polynomial. Next, how about eigenvectors? And it's going to be the same. If you have two matrices that are similar, then they have the same eigenvalues, but they don't have the same eigenvectors. Let's try to prove that by using this particular example. A is a square matrix. This is something that we have seen before. We evaluated its eigenvalues, eigenvectors. Let me also prove. I forgot to mention one more thing. If I go back to my diagonalization example, I diagonalize A into this D, right? I diagonalized A to get D, and to diagonalize A, I constructed a square matrix which had columns that were eigenvectors of A. But what the result that I got actually had two non-zero values in my diagonal, 2 and -1. Those are actually the eigenvalues of A. So we not only get a diagonal matrix, in fact, our diagonal elements will be lambda 1, lambda 2. So I can make this, say, lambda 1 here, lambda 2 here. So that's what we are getting here, lambda 1 and lambda 2. All right, so let's go back and take a look at this. Right, so we got we are trying to prove that if they are similar, then that does not imply that they have the same eigenvectors. So A square matrix, as before, we have got two eigenvectors for it that correspond to lambda 1 equals 2, lambda 2 equals -1, and we were able to diagonalize it, and the diagonal matrix was this. We have actually seen this before. We have eigenvalues in the diagonal. All the off diagonal elements are 0, but this guy has uh, the unit vectors as the eigenvectors. So if you take B, because it only has diagonal elements, and you try to go for if you try to make determinant of B minus Ti, set it to 0, you get a characteristic polynomial. You take the roots of that characteristic polynomial and you evaluate a minus lambda I x equals 0, form an augmented matrix, do the row reductions. All of that will give you two eigenvectors, and you will see that those two eigenvectors are unit vectors 1 0 0 1. But there's a simpler way to sort of look at this, which is if I take this particular matrix, right? So if I take this matrix here, 2 0 0 -1, I'm going x, right? So if I take any vector here, x, it is going to give me some scalar lambda 1 times the same thing, x. And because these elements are 0 over here, 1 0 will satisfy that, and you will get some lambda 1 for that. And similarly, if you take the other case here, which is 2 0 0 -1, and you multiply it with say 0 and 1, you will get some lambda 2. It'll be the same lambda 2 because these are similar. The eigenvalues will be the same. So you should get a 2 there, and you should get -1 over there. And 0 1 will satisfy this. So the unit vectors will be eigenvectors for B because it's a diagonal matrix. It'll have the same eigenvalues, but as you can clearly see, the eigenvectors for B are unit vectors. Eigenvectors for A are not unit vectors, which essentially proves this. Similar does not mean same eigenvectors. All right, let's move on to another example where we are looking at similar matrices. So we have A over here, another matrix B. They are both square matrices, and these are similar matrices. And let us actually try to see whether they are in fact similar or not. So the claim is that they are similar. So if I take S, some matrix S, which is right now considered as 0, 5, 3, and 4, I will also evaluate S inverse. So I have a 2 by 2 matrix. I can quickly find the inverse of that by doing 1 over the determinant, and then switch the diagonal elements and multiply the off diagonal elements by a -1. I got S inverse. Now you can check whether S actually satisfies this, right? So if two matrices are similar, then you know that this condition has to hold true. So you can take S inverse from here, you can take A from the original matrix, S from here, and if you multiply it out, do you get B or not? If you do get B, then you can say that A and B are similar matrices. So I'll leave that as an exercise for you. But this actually involves computing S inverse. But there's an alternate way to look for similar matrices, which is simply this: AS equals SB. So the product of AS should equal, AS is right here, and the product of BS is going to be here and here again. Those two should give you, SB should give you the same thing. And we can look at it. So if you look at this, so if I have S inverse here, A here, S here equals B, I can multiply with S on both sides. So I've got S here and I've got S here. And then this gives me an identity here. So that can go away. So all you're left with is AS equals SB. So the product of AS will give you a squared matrix here, 0, 10, 6, 23. And if you did SB, it'll also give you the exact same matrix. So if you prove this, you are equivalently proving that, which means that the claim over here is in fact true. A and B are similar matrices. Now, what we saw earlier is that A is not similar to any diagonal matrix. So here A, we looked at earlier, the same matrix, it was not similar to any diagonal matrix here. So even though A is not diagonalizable, it still has a similar matrix. All right, let's move on here. Look at diagonalization. So we'll talk about why is diagonalization useful. It is useful for two reasons mainly. One is obtaining the characteristic polynomial is pretty convenient. Characteristic polynomial is easy to find because what you will have is only elements in the diagonal, right? So if you did 2 minus ti and minus 1 minus ti and you have to do the product of that, you can ignore all the other elements because they are anyway 0. So the characteristic polynomial for a diagonal matrix such as this is pretty easy to compute, which makes a diagonal matrix convenient to work with, and it is going to have the same eigenvalues as your original A matrix, right? So you're not changing the eigenvalues. Now, that's one benefit. The other benefit of diagonalization is looking at higher powers of A. Right. So if you look at this, if I raised A to say A squared, A cubed, A to the 10, A to the 100, then I'm actually going to spend a lot of time doing matrix multiplications. As I increase the power of A to a very high value, I'm going to increase my computation time for evaluating the product of all those matrices, because A is not a diagonal matrix. However, if we had a diagonal matrix, and this relation will hold true, and we'll prove this. You see, if you want to raise A to the power of k, right, really high power of k, the claim here is it is the same thing as evaluating S. You're not raising S to any power. S inverse, you're just computing the inverse of S. But taking the diagonal matrix and raising it to a high power k, all we need to do for that is take the elements in the diagonal and raise it to k, right? So you don't have to do all of that matrix multiplication. So that's your second benefit of diagonalization. So let's take a look at how do you diagonalize and what are the conditions for a matrix to be diagonalizable. So we saw earlier that our square matrix 3, minus 2, 2 and minus 2 is diagonalized by this particular matrix S, which contains two columns. These two columns correspond to the two eigenvectors of A, one corresponding to eigenvalue 2, the other corresponding to eigenvalue -1. And what we got is S inverse AS gave us a diagonal matrix which was diagonal with the two elements in the diagonal corresponding to the eigenvalues. So this is a diagonal matrix containing the eigenvalues of A on the diagonal. Now, A can be written as SD S inverse. How can you do that? Well, the same as before, right? So if S inverse AS equals D, then I need to sort of get rid of these two guys. So what I'm going to do here is multiply with a S here, multiply with S inverse here, which means I also need to multiply S here and S inverse here. So what I'm left with is A equals SD S inverse, right? So if A is SD S inverse, because that's we know that condition holds true, A, we diagonalized it to get D. Now take a look at what happens when you raise A to a higher power. So let's start with squaring A. So if you square A, then you are literally taking A and multiplying it, right? So A is SD S inverse, you have SD and S inverse here, you have SD S inverse here. So you've got A here, and you've got A here, and you're now multiplying them. Now, once you start multiplying them, I know that it is associative, so I can rearrange the parentheses without changing the order. So what I'm doing is I'm bringing this parentheses here, bringing this guy over here, pulling out SD, S inverse S from the middle remains as is, and then you have D S inverse all the way at the end. I'm just rearranging the parentheses. I'm not changing the order of how the matrices are laid out here. So that should be okay. Now, if you look at this, you have got S inverse S, which is simply an identity matrix. So that can go away. What you're left with is S D squared S inverse, right? So all you're left with is S D squared S inverse. So when you're going for A squared, what you got is S D squared S inverse. The only thing that got raised to a higher power was D, a diagonal matrix, which is pretty easy to compute. So if you generalize it, you try to look at A cubed, A to the 4, and so on, what you can say is A raised to any high power K greater than a positive integer is going to give you S D raised to K S inverse. But this one is easy to compute. So you're not multiplying matrices K times. All you're doing is computing S inverse, and then literally raise D to the higher power. Essentially means the elements in the diagonal get raised to that high power K. So that's another benefit of diagonalization. Next, let's calculate A raised to K times. Let's do an example here. When we try to raise some matrix A to the 9th power with vector V that is given as 1, -1. So our example over here is A, the same square matrix A with eigenvalues 2 and -1. It is diagonalized using this particular matrix S, which contains 2 eigenvectors, 2, 1, 1, 2. And we already saw that S inverse AS gives us a diagonal matrix with the diagonal elements corresponding to the eigenvalues of A. We already saw that. Now, when you want to find, say, A raised to 9 times V, where V is given to be this particular vector, you need to find this, right? A raised to 9 times V. Well, you can include V later, but what is critical here is if you want to find A raised to 9, what you're really trying to do is you're trying to find this S D raised to 9 S inverse. And it's going to be pretty easy to do this instead of multiplying A 9 times, we can actually do this very easily. And let's take a look at that. You have got S here. S is right here. Actually, S is right here. And then this guy is S inverse with this. And then you have D raised to 9 right here. And then, of course, we have the V getting multiplied way at the end. So you have S, D raised to 9, S inverse, and then V. So if you want to raise a diagonal matrix to the 9th power, all you do is raise each element in the diagonal to the 9th power. So 2 raised to 9, 5, 12, -1 raised to 9, -1. Everything else remains as is. Carry out the multiplications now. Pretty straightforward. You get your answer pretty quickly, as opposed to doing this A raised to 9. So this is what makes it very convenient. Next, let's see. All right, diagonalization. So when can we diagonalize a matrix? So some theorems here, and we'll try to look at some more details as we go on. So the definition of diagonalizable matrices is this. A square matrix A is diagonalizable if it is similar to a diagonal matrix. So what we need is this. What we need is, if A is diagonalizable, then this condition has to be true. S inverse has to give me some diagonal matrix D. So for some square matrix S, if I post multiply, sorry, this I've written it wrong. This is like S inverse AS has to give me D. If that is true for a square matrix A, if I'm able to get a diagonal matrix, then that matrix A is considered to be diagonalizable. Now, a theorem based on this is A is diagonalizable if and only if it possesses n linearly independent eigenvectors. So the eigenvectors that A should have are going to be linearly independent eigenvectors, where n is essentially your size of the square matrix. And I'm not going to go to the proof. You can take a look at the proof in the text. So what are you going to have? Well, S inverse AS equals D. What does it have? Well, I'm going to write that again over here. S inverse AS equals D. Well, how did we make S? We made S by looking at columns of eigenvectors of A, right? So this S contains columns of eigenvectors of A. And when we carry out that multiplication, S inverse AS, you get diagonal matrix. And diagonal matrix has all elements 0 except for the diagonal elements. The diagonal elements are what? The eigenvalues of A. Right? So this guy, diagonal entries are eigenvalues of A. So these two statements are actually captured over here. The columns of A are the eigenvectors of A, typo. Columns of S are eigenvectors of A, and then the diagonal matrix that you get on the right side D is contains the eigenvalues of A in the diagonal. Everything else is a 0. Now earlier we saw that there was a non-diagonalizable example, right? We proved it by contradiction. We said something like this is true, and then when we tried to do it, our result was contradicting the assumption. So we know that this particular matrix A, a square matrix, is non-diagonalizable. Now, another way of looking at whether you can diagonalize a matrix or not is by looking at whether it is defective or not. So you're trying to compare the algebraic multiplicity with the geometric multiplicity. So if you look at this particular matrix A, we already know that it is not diagonalizable. We'll also look at the fact that it is defective. It is in fact defective because if you look at the characteristic polynomial of A, what do you have? Determinant of A minus Ti equals what? 2 minus T whole squared. So you're taking a look at this, you're doing a minus T there, your minus T there, find the determinant. You will see that it is going to be 2 minus T squared, because when you do this, it's a 0, right? So you have nothing to subtract there. So 2 minus T squared, what do we know about that? There is a eigenvalue. The eigenvalue is 2, right? So with this, you know that there is an eigenvalue 2 with algebraic multiplicity of 2, right? Multiplicity of 2. But we are going to see that the geometric multiplicity for this, which is the dimension of the eigenspace, is actually just 1. So we'll try to add a page here and take a look at that. So we are looking at, there's only one eigenvector, right? Eigenvalue. 2 is your eigenvalue, lambda equals 2. And we are trying to find the geometric multiplicity, and we are going to do that by looking at A minus 2i x equals 0. So we'll set up this augmented matrix A minus 2i x equals 0. What is A minus 2i? So A is right here. When you do minus 2i, this will go away, this will go away. So essentially what you have is 0, 0, 0, and then 3, 0, 0. That's it. That's your augmented matrix. Now you can, quickly switch the column, switch the rows, divide the first row by 3, you get 1 0 0 0 0 0, and now you start reading off the solution. Let's say that x1 equals, you know that x1 equals 0 because of this guy, and then x2 can be anything. So what you have is the vector x is x1, x2, which will be 0t, which will be t times 0, 1. So the dimension over here for my eigenspace is only 1. So I only have one vector in the basis of my eigenspace. So this is captured over here. The eigenspace has a dimension of 1 with the basis 0 and 1. So I've got algebraic multiplicity of 2. Geometric multiplicity is smaller than that, 1, which means that it is a defective matrix. And for defective matrices, they are not diagonalizable. Let's move on. Take a look at diagonalization and eigenvectors. So we have an n by n square matrix A. It is diagonalizable if there exists an invertible matrix S such that S inverse AS equals D for some diagonal matrix D. We already saw that. Now, it is also considered to be diagonal if it has n linearly independent eigenvectors, V1 through Vn. So these two conditions were actually listed over here. So one condition was it is diagonalizable if there is some S that exists to make A diagonal. The other one was a theorem which states A is diagonalizable if it has n linearly independent eigenvectors. So, and those eigenvectors over here we are considering as V1 through Vn, n linearly independent eigenvectors. So if the eigenvectors are there, now the question is, why do the eigenvectors work? So why is it that you can take eigenvectors and arrange them as S and S inverse, and how are you able to get a diagonal matrix? Why are the eigenvectors working? So for this, what I'll do is I'll add another page here and try to consider. I also know that what diagonalization S inverse AS equals D can be equivalently written as AS equals SD. You are simply post multiplying by S here, S here, S inverse gets cancelled. You are left with AS equals SD, right? It's the same thing as saying that. S we are constructing using the n independent, linearly independent eigenvectors of A, V1 all the way to Vn. So let us try to look at the product AS. Let us try to take a look at the product SD to just prove that eigenvectors are actually helping you diagonalize. So let's do that over here. So here I will first consider the product AS. So if you have AS, what do you have? You have the matrix A, and S is a matrix whose columns are eigenvectors. So I'm going to say that these are V1, V2, so on up to Vn, and these are column vectors here. And I'm trying to multiply, so that's A and that's S. If I multiply it out, what do I get? A is n by n, right? This guy is n by n, and V1 and V2 and V so on are what? N by 1, n by 1, and so on, n by 1, right? So when I multiply A with V1, what do I get? I get a n by 1. It's going to be a column vector. AV1 is going to be a column vector. So the first one will be AV1, next will be AV2, so on up to AVN. And again, these are going to be column vectors here. So that's AS. Now, because we know that V1, V2, V3, and so on up to Vn, these are eigenvectors of A, we can write AV1 as lambda 1 V1, right? So if you use the fact that these are eigenvectors, instead of AV1, I can write lambda 1 V1 and so on. So lambda 1 V1, lambda 2 V2, lambda n Vn, where lambda 1 and so all the lambdas are eigenvalues that correspond to the eigenvectors V1 through Vn. Again, these are all column vectors. Next, that's the result for AS. Now take a look at SD. If you look at SD, right, what do you have for S? Well, the same thing as before. V1, V2, so on up to Vn. Columns are eigenvectors of A. How about D? For D, I have, it's a diagonal matrix. And what are the entries in the diagonal? Those are the eigenvalues, right? So it is lambda 1, lambda 2, so on up to lambda n. Everything else is a 0 there. So when you multiply this out, what do you have? You will get the same thing as AS. You are going to get lambda 1 V1, lambda 2 V2, so on up to lambda n Vn. And these are all, again, column vectors. So you can see that AS equals SD, which also proves that S inverse AS equals D, and it was diagonalizable when you used S as the eigenvectors of A. That is the reason why the eigenvectors are able to help us transform a matrix A into a diagonal matrix. So all of those conditions are essentially listed over here. We considered AS, we wrote that as product of AV1 and so on. Then we use the fact that these are eigenvectors. So AV1 can be written as lambda 1 V1 and so on. And we also looked at the product SD. S is columns are eigenvectors of A. D is a diagonal matrix with the diagonal entries to be eigenvalues. When you do the product, you get these two to be exactly the same, which means that the eigenvectors are going to be able to help us transform a matrix A into a diagonal matrix. We are able to diagonalize that matrix A with S. All right, let's move on here. We looked at that. Next, we have distinct eigenvalues. So the next thing that we are going to look at is, do I have distinct eigenvalues, or do I have repeated eigenvalues, and does that have anything to do with being diagonalizable? So and it is connected to diagonalizable or not using defective matrices. So I know that if all the eigenvalues are distinct, they are all different, then I know that the matrix is not going to be defective, because if you have all the distinct eigenvalues, then their algebraic multiplicity will be 1. And if the algebraic multiplicity is 1, then we know that geometric multiplicity has to be 1. And we have looked at that before. Only when the algebraic multiplicity is greater than 1, then you need to sort of worry about what the geometric multiplicity is. But if you have all distinct eigenvalues, you know that the matrix is not going to be defective. Right? So we make this statement. We saw earlier that a matrix is not defective if it has n distinct eigenvalues. I don't need to worry about that. But only when it has repeated, then I need to worry about that. However, it is possible that you may have repeated roots, right? You may have repeated roots, which means that you have repeated eigenvalues, but you still may have a diagonalizable matrix. And we'll take a look at an example over there. So this is a sufficient condition, but it is not a necessary condition. You're right. So we can make the statement here. What we are using here is this. We are using the fact that if algebraic multiplicity equals 1, that also implies that geometric multiplicity equals 1. And if algebraic multiplicity and both of them are 1, we know that the matrix is not defective. And if it is not defective, then you will be able to diagonalize it. So it will be considered a diagonalizable matrix. So A is diagonalizable if and only if it is not defective. However, we have to be careful about this, which is if you have non-distinct eigenvalues, so if you have repeated eigenvalues, that does not mean that it is not defective. And hence, it does not mean that you cannot diagonalize it. You can still diagonalize it. And we'll take a look at some examples. So here we have an example for the straightforward case, which is distinct eigenvalues. So when you have distinct eigenvalues, you already know that it should be fine. We should be able to diagonalize it. And when you diagonalize it, you should get your diagonal elements to be exactly the same as the eigenvalues of A. So here we have A as our 3 by 3 matrix. And when we are going over the conversation about eigenvalues and eigenvectors, characteristic polynomial, setting up the augmented matrix A minus Ti x equals 0, doing all of that, we have already seen that you will get 3 eigenvalues for this. They are all distinct, 0, 2, and 4. And the way you're getting this is, remember, you're doing determinant of A minus Ti, set it to 0, find the roots, and you get this, right? Or you can do lambda. Find the roots of that, you will get, for this particular 3 by 3 matrix, you will get 0, 2, and 4. And we also found for each of these eigenvalues, we found the eigenvectors. We got 3 eigenvectors, one for each case, 0, 2, and 4. These are 3 eigenvectors, and clearly they are independent eigenvectors. So we have 3 independent eigenvectors. We right away know that A should be diagonalizable because we have 3 independent eigenvectors. And S actually is the matrix S, the square matrix S, which is constructed using the eigenvectors. V1 goes here, and then V2 goes here, and V3 goes here. Right, so for all of these, how are you setting up the eigenvectors? Eigenvectors are being set up by A minus lambda I x equals 0. You're trying to find the vectors that are in the null space of A minus lambda I when lambda is 0, 2, and 4. And when you solve for that, those vectors in those 3 cases, the null space, you will see that you will get, when lambda is lambda 0, you get V1, 2, you get V2, 4, you get V3. And with these 3 eigenvectors, you are arranging them as columns of S. So now is S going to diagonalize our matrix A? And the way we check that is, and the diagonal matrix D is going to be what? It is going to be diagonalized, which means that all the off-diagonal elements are 0, and the only elements that are in the diagonal are the eigenvalues 0, 2, and 4. So how can you check this? Well, AS equals SD, or you can say S inverse AS equals D, whatever. If you do if you do the other check, S inverse AS equals D or not, if you do the other check, then this involves sort of inverting a 3 by 3 matrix, which may be time consuming. So instead, what you can do is just do this, right? AS equals SD. Does it equal or not? So you have S from here, you have A from here, S again is here, and D is here. Multiply it out both right and left, and if they are the same, you know that A was diagonalized to D using S. So here is an example where you have distinct eigenvalues, where the matrix A with those distinct eigenvalues was diagonalizable. And you can check this later. Let me move on to repeated, right? So next, like I said, if it had repeated eigenvalues, then it does not mean that it is not diagonalizable. Let's try to prove that with this particular example. Here you have a 3 by 3 square matrix. We can find the characteristic polynomial for this doing A minus Ti. And if you do A minus Ti, you get 2 minus T squared and minus 3 minus T. Essentially, it gives you three eigenvalues. Two of them are repeated. So two of them are 2. One of them is -3. If you look at the eigenvalue 2, for this case, the power over there is 2. For lambda equals 2, the algebraic multiplicity is 2, but also the geometric multiplicity is also 2. So lambda equals 2 gave you both geometric as well as even algebraic multiplicity equals 2 because of this guy. And we can see that its geometric multiplicity is also 2. Let me quickly take a look at that. So what am I doing? This is for lambda equals 2. So I'm setting up a minus 2i times x equals 0. That's my augmented matrix. Then I'll do row reductions and see what I get for the geometric multiplicity. Essentially, how many vectors do I have in the basis? Null space of a minus 2i. So let's take a look at that over here. I've got a as 4. So all of this gets multiplied, subtract by 2 here, 2 here, 2 here. So when I do a minus 2i times x equals 0, that essentially gives me the augmented matrix 2 1 3 0 4 2 6 0 -6 -3 -9 and 0. And you can see that the second row is a multiple of the first one. The third row is also a multiple of the first one. So you can do row reductions to get rid of the second and the third row. So if you did something like this, let's see, row 2 minus 2 times row 1, and you did row 3 plus 3 times row 1, what you get is only the first row. Everything else will go to 0. Now we can start looking at the solution. Now the solution will be what? You can say based on this first row, you can say 2x1 plus x2 plus 3x3 equals 0. Now we can set this. We can set, say I set x2 to be some s, and we set x3 to be some t. What that implies is x1 is going to equal -1/2 s and -3/2t. And now if I look at the basis, what do I have? I have x vector is x1, x2, x3, which is going to be, say, s. I can do -s times -1/2, and then for the next one I'm going to get -1 here, and there's nothing, no s in 3, so 0 there. And then for the other one I can say plus t. How much t is there in x1? -3/2, and then s2 has nothing and x3 has 1. Now what I can do is multiply these out. So here I can get rid of this, this, and this. Sorry, I may have made an error here. When I do -s, right, this one will be, here, let me take a look. If I do -s here, I get this to be negative, this to be positive. All right, and then you're right. So if I try to get rid of the -s there, I can make that positive, make this negative, make this positive, and then t, I can leave that as -3/2, and I can multiply over here by say -2, -2, -2, and what I'm left with is 2 eigenvectors. This guy gives me and I can multiply this even by 2, right? So I can multiply 2 here, 2 here, 2 here. Because I'm looking for the basis. Any multiple of that basis is also going to be there. So I've got -1 for S. Then I've got 2, then 0. And the second one is 3, 0, -2. Those are my two vectors. This corresponds to this corresponds to that second one. So I've got two basis vectors here. Dimension is 2, which means my geometric multiplicity is 2. So these are essentially laid out over here and here. I've got my basis with these two vectors. Geometric multiplicity is 2 equals algebraic multiplicity, which also implies that it is not defective for lambda equals 2. Next, let us try to look at lambda equals -3. So when you have lambda equals -3, well, it just has 1 as your algebraic multiplicity, so I don't even need to check. I know that its geometric multiplicity is also going to be 1, so it is not defective. What we get is the matrix S that diagonalizes A is going to be the vector, the square matrix with vectors, the columns as eigenvectors. So we've got negative, the first one here, the second one here, and then from the other eigenvalue, you've got this guy over here. So with this S, the claim is that you can diagonalize A. So you can check that again the same way. AS, is it equal to SD or not? And D, what are you going to have? It's going to be a diagonal matrix with all the off diagonal elements 0. In the diagonal, you're going to have the 3 eigenvalues, 2, 2, and -3. So that's your D here. So with this S, you should be able to diagonalize A to this D, check this condition. So this essentially proves that if you have repeated eigenvalues, that does not mean A is not diagonalizable. But what we can say, the sufficient condition is that if it has distinct eigenvalues, then it will definitely be diagonalizable because it will not be defective. But if you have repeated eigenvalues, then you have to check for whether the matrix is defective or not. We did this. Yeah, we did this. Now, what about complex eigenvalues? So with complex eigenvalues, say we have this matrix A, let us take a look at its eigenvalues and eigenvectors. Can we diagonalize a matrix which has complex eigenvalues? So here we have a matrix A, square matrix. Find the eigenvalues, determinant of A minus Ti, set it to 0. You will see that you will have two eigenvalues, plus and minus I. And again, it's consistent with our discussions from earlier, where the eigenvalues are appearing as complex conjugates of each other. The two eigenvectors that you're going to get for this are V1 and V2. And this is an example that we've already seen before. And over here, what do you have? I1, negative I1. So eigenvectors are also complex conjugates, consistent with our discussion earlier. So I'm going to construct this square matrix S, which has these two as the columns. One for lambda equals plus I, one for lambda equals minus I. And if it is diagonalizable, then I should get in the diagonal I and negative I, the off diagonal elements are all 0. So here you have the eigenvalues. Let's see. Let me and okay, if this is all true, then this has to be true, right? So if the claim is true that you can in fact diagonalize a matrix with complex eigenvalues, it should be able to satisfy this. So if you compute AS, you will get this matrix. You compute SD, you will get the same matrix here, which proves that matrix S was able to diagonalize the matrix A, even if it has complex eigenvalues. And again, when you're thinking of why we are diagonalizing things, you have that motivation. Characteristic polynomial is going to be easy to find. Eigenvalues are going to be easy to find. And raising a matrix to a higher power is going to be easy to compute if it is diagonalizable. So we'll take a look at a later slide where you see if you are trying to find eigenvalues of a matrix which is not in the diagonalized form, the characteristic polynomial and finding the roots is going to take a long time. So instead, if you look at the diagonalized version of the same matrix, you know that they're going to have the same eigenvalues. So we'll try to work with that instead. All right, next conversation is about orthogonal matrices. So these are special matrices that are going to help us diagonalize things. Symmetric matrices can always be diagonalized. So we are going to discuss in the next section that if you have symmetric matrices, you can always diagonalize them, and they can be diagonalized using orthogonal matrices. So for orthogonal matrices, this particular condition has to be true. And the letter that we use for orthogonal matrices is Q. So if a matrix Q is orthogonal, then Q is invertible, and in fact its inverse is the same as its transpose. So if a matrix satisfies this criteria, inverse of the matrix and the transpose of the matrix are exactly the same, then that is going to be an orthogonal matrix. And using an orthogonal matrix, we can diagonalize any symmetric matrix, which means symmetric matrix is A equals A transpose. So using orthogonal matrices, we can diagonalize symmetric matrices. But this condition has to be true for that. So you see, earlier what were we doing? We were earlier looking at S inverse A S equals D, right, to diagonalize A. Now, with orthogonal matrices, you are looking at Q inverse A Q equals D. But because this condition, Q inverse is Q transpose, what you can do is use Q transpose. So A is diagonalized using orthogonal matrix if it satisfies, if there is some Q, some orthogonal matrix that satisfies this criteria. Q transpose AQ equals D. Let's try to take a look at an example of an orthogonal matrix. We have Q, all the elements are given to you over here, and the claim over here is that Q is an orthogonal matrix. So take a look at its transpose, take a look at its inverse, they should match. Or what you can do is simply take a look at its transpose. It's very easy to switch the rows with the columns. Then try to look at the products here. If you look at Q transpose or Q transpose Q, you will get identity matrix. So if you take Q transpose, if you do the product Q with Q transpose and it is giving you identity, that essentially means Q transpose is the inverse of Q, right? So if you look at this actually implies this, Q transpose equals Q inverse. And with these matrices, you can perform the matrix multiplication to check whether this is true for this Q matrix or not. So orthogonal matrices are really helping us diagonalize symmetric matrices. All we have to do is find a Q that satisfies this. Next, the columns. What can we say about the columns of an orthogonal matrix? So I'm going to first consider an orthogonal matrix. Once I consider an orthogonal matrix, I know that this particular condition it's going to be satisfied. Q transpose Q should be equal to I. Now I'm going to look at the columns of the orthogonal matrix. So I'll use Q1, Q2, Q3, and so on up to Qn as columns of the orthogonal matrix. And I'm going to take a look at the product Q transpose Q. So I will add a page here and start looking at the product Q transpose Q. Q is my orthogonal matrix whose columns are Q1, Q2, Q3, and so on up to Qn. So if Q transpose Q is going to be what? This is going to be Q transpose. So I've got Q1 transpose, Q2 transpose, so on up to Qn transpose, right? That's for Q transpose. That is getting multiplied with Q. What is Q? Q is simply Q1, Q2, so on up to Qn. These are columns. If I'm going to multiply this, what do I have? Q1 transpose Q1, right? So Q1 transpose Q1 as my first element, Q1 transpose Q2 as my second element, Q1 transpose Q3 and as my third element. So essentially you're trying to find the dot product of Q1 with all of these columns to get my first row. So when you simplify this, when you carry out the multiplication, what are you going to get? For the first one, you're going to get Q1 transpose Q1, then Q1 transpose Q2, and so on up to Q1 transpose Qn. What will you get in the next row? You will get Q2 transpose Q1, Q2 transpose Q2, so on up to Q2 transpose Qn. And similarly, if you go down here, you're going to get the last one will be Qn transpose Q1, next Qn transpose Q2, so on up to Qn transpose Qn. So Q transpose Q, when you actually have Q set up as column vectors Q1 through Qn, consider the product Q transpose Q. It's going to give you this particular square matrix, n by n square matrix, where each element over here is a dot product of Q1 with Q1 or Q2 with Q2, Q1 with Q1, Q1 with Q2, and so on. And then you get all the other elements. But the claim is Q is orthogonal, right? So if Q is orthogonal, then it has to satisfy this criteria. Q transpose Q should be equal to I. Now, if you look at that, this has to equal an identity matrix. 1, 1, so on, 1, and everything else should be a 0. Q transpose Q should be equal to identity matrix. So, what can we say about these guys? This, all of these guys should be equal to 1, right? And everything else should be a 0. So, based on that, what we can say, sorry, this is not 0, this is 1. Everything else is a 0. So what based on that we can say Q1 transpose Q1 should equal Q2 transpose Q2 and Qn transpose Qn should all equal 1, and then Qi transpose Qj should equal 0 if I doesn't equal j. And the product of Q transpose Q, because of all these elements being represented as a pattern, you can also write this as, when you Q transpose Q, the I comma jth element here is going to be simply Q transpose I Qj, right? So what we have is an orthonormal basis, right? All of these guys are 1, all of the other elements are 0. So in Q1 through Qn, these column vectors are essentially our orthonormal basis. They are normal because the norm is 1 for all of them, and they are orthogonal because the dot product with everybody else is a 0. So what we can claim here is Q1, Q2, Qn, these are going to form an orthonormal basis for R to the n. So if I go back here, this is what I'm saying over here. So the I comma jth entry is going to be equal to the dot product between row I and column j. But because I'm using row I of q transpose, row I of q transpose is the same thing as saying column I of q. So you're doing a dot product between column I of q and column j of q, and that should give you an identity matrix because of that condition. So when you take the dot product, it will be equal to 1 when I equals j, the diagonal elements, and it is going to give to 0 if I is not equal to j. That's what we did over here. We compared this matrix here with an identity. Q transpose Q should give you identity because it is orthogonal. You compare them, you can say that the dot product of two vectors with itself is a 1, with every other vector is going to be a 0. And the norm here is going to be 1 for them. So orthonormal vectors. So that leads us to this theorem, which is the columns of an orthogonal matrix here are going to constitute the orthonormal basis for R to the n. Now, why is it the basis, and why is it orthogonal, and why is it orthonormal? So for that, let me just add a page here and write why orthogonal. We said this is an orthonormal basis for R to the n. So why basis, why orthogonal, why orthonormal? Orthogonal because qi transpose qj equals 0 when I doesn't equal j, and orthonormal because qi transpose qi equals 1 for all I, and it is a basis because columns are linearly independent, and we know that because Q is invertible. And its inverse is its transpose. All right, so let's go on here. Look at permutation matrices. So what are permutation matrices? These are orthogonal matrices in which you can switch around the switch around the columns. So we can permute the columns of an orthogonal matrix, and it will still remain as an orthonormal basis for R to the n. An example for a permutation matrix is an identity. Identity is an orthogonal matrix, so you can permute the columns. So reordering the columns of an identity matrix gives you a permutation matrix. And the claim over here is it still remains as an orthogonal matrix. It will form the orthonormal basis for R to the n. So if you have an identity matrix, you can switch around the columns. So here we have placed the first column in the second column place, the second column in the last column place, and the last column we have brought it up front to made it the first column. So this is going to be a permutation matrix that corresponds to a 3x3 identity matrix. So still you get an orthonormal basis for R to the n. Permutating columns. Next, some interesting properties of orthogonal matrices. The first property is, what are we giving? We are considering that Q is an orthogonal matrix. So that means that its inverse is the same as its transpose. The length doesn't change. If you have a vector x in R to the n, its norm is not going to change even if you multiply it with an orthogonal matrix Q. So it may look different, right? When you multiply it with Q, an orthogonal matrix, it may look different, but when you calculate its norm, its distance, it is going to be exactly the same. And you can actually prove this pretty quickly by looking at, I'm going to prove this over here. So for this, I will consider the norm squared of Qx. Q is an orthogonal matrix, X is a vector in R to the n. I'm considering the square of the norm here. I can write this as Qx transpose times Qx, right? The square of the norm is A transpose A. So in this case, A is Qx. So Qx transpose times Qx. Now, what do we know about the property of transpose? You can arrange it. Reverse the order, right? So when you reverse the order, you get X transpose multiplied by Q transpose multiplied by QX remains as is. Now, what do we know about Q transpose Q? Well, Q transpose is the same as Q inverse because it's orthogonal. So this will simplify down to X transpose X, which is simply the norm of X squared. So this proves that if you have any vector X in R to the N, if you multiply with an orthogonal matrix Q, you don't change the length of the vector. Even though it may look different, you don't change the length of the vector. The second property of orthogonal matrices is if you have, say, two vectors x and y, and you look at the result, you look at the dot product of qx transpose with qy, it is the same as x transpose y. And to prove this, we have the proof over here. Consider the product qx transpose with qy. X and y are two vectors in R to the n. Q is the orthogonal matrix. Again, using the same reasoning as before, qx transpose can be written as q transpose q transpose x transpose q transpose. So when you transpose you reverse the order there, qy remains as is. Next, you have q transpose multiplied by q, giving you an identity because it's an orthogonal matrix. Q transpose equals q inverse. You're left with x transpose y. Next, the determinant of q will either be plus or minus 1. So let's take a look at that. Over here, consider the square of the determinant of q. We can write this as determinant of q transpose multiplied by determinant of q, right? So we have determinant of q multiplied by determinant of q. And determinant of q, we know that it is going to be the same as determinant of q transpose. When you switch around the rows and the columns, the determinant doesn't change. So instead of writing determinant q twice, we are writing one of them to be determinant of q transpose. Now, when you have determinant of q transpose multiplied by determinant of q, you be looking at the properties of determinants. Determinant of a times b is the same as determinant of a multiplied by determinant of b. So using the property in reverse, you can combine them and write as determinant of q transpose q. Q transpose equals q inverse. So what you really have is determinant of an identity matrix, which equals 1. So the determinant of q is going to be plus or minus 1. The determinant of q, any orthogonal matrix will be plus or minus 1. So 3 properties of orthogonal matrices. Next, finding eigenvalues of larger matrices. So we're not going to have this on the exam, but I'm just trying to point you to how do you deal with really large matrices. Say you want to find the eigenvalues, right? You want to find eigenvalues of very large matrices. So the one technique that we have seen currently is go for the characteristic polynomial, and as the size of the matrix becomes large, the order of that polynomial, characteristic polynomial, is going to increase. Finding the roots of that characteristic polynomial is going to become very cumbersome. So this is not a practical approach to deal with larger matrices. So what we are going to leverage is orthogonal matrices and the idea of similarity. So if two matrices are similar, we know that they will have the same eigenvalues. So we can try to use orthogonal matrices Q to introduce zeros in your original matrix A. When you start introducing zeros and then you look at Q transpose AQ, which is you're diagonalizing that matrix, it is going to be a sparse matrix. You're going to have a lot of zeros, and looking at the roots of this particular characteristic polynomial is going to be much easier to compute. So if you have a larger matrix, instead of computing the eigenvalues of the large matrix directly, you try to use orthogonal matrices so that to introduce a lot of zeros, and then because they are similar and similar matrices have the same eigenvalues, you can deal with a much sparser matrix B instead of the not so sparse matrix A. The details are in the textbook in chapter 7. not going to be part of the final exam, the second exam. Next, diagonalization of symmetric matrices. So how do you diagonalize symmetric matrix? We have already said that symmetric matrices should always be diagonalizable. How can you do that? Well, if matrix A is symmetric, there exists a matrix Q such that Q transpose AQ will give you D. So earlier we were looking at, S inverse AS equals D. Now we are using, instead of S, we are using orthogonal matrices to diagonalize A. And instead of saying Q inverse AQ equals D, because it's an orthogonal matrix, you can simply say Q transpose AQ equals D. So that's what we have over here. You can see the textbook for the proof, but this is what orthogonally diagonalizing means. So A can be orthogonally diagonalized by using orthogonal matrix Q. So you're given a matrix A which is symmetric, and you are converting that into a diagonalized matrix using orthogonal matrix Q. So that can be orthogonally diagonalized. What we have already seen that the columns of Q are eigenvectors of A. This gives us the following corollary, which is A is symmetric, then there exists a basis for R to the n that consists of eigenvectors of A. Now with the, well, I'll come to, and we'll deal with some examples here. How do you diagonalize a symmetric matrix? And I'm going to relate that to one of your problems on homework 10, for which there is some confusion. So I'll try to relate that here. So let's take an example here. We are trying to get an orthogonal basis of our eigenvectors. We have a symmetric matrix A. We want to find the orthonormal basis of eigenvectors for this symmetric matrix A. But so if we have a symmetric matrix A equals A transpose, we can try to find its characteristic polynomial, eigenvalues, eigenvectors, and so on. Let's try to do that. We have the characteristic polynomial can be obtained by evaluating the determinant of A minus Ti. Here you will get order 3 polynomial. You have 2 repeated eigenvalues at 3 and 1 distinct eigenvalue at 9. The moment you know that one distinct value of 9, you know that the algebraic multiplicity here, which is 1, is going to equal your geometric multiplicity. So if you then evaluate, say, A minus 9i x equals 0, then you can look at the null space of A minus 9i. It will have a dimension of 1, only one vector in its basis. Some arbitrary value t times 1 to negative 1. That is for the first eigenvalue here, 9. But for the second eigenvalue, you are going to have repeated roots here. So the algebraic multiplicity is 2. Let's take a look at what is the basis here of null space of A minus 3i. So you, just as you considered A minus 9i times x equals 0, now you're considering for the second lambda, which is 3, you're considering A minus 3i x equals 0. Form the augmented matrix, do the row reductions to get the matrix in the row reduced echelon form. From here, you can read off the solution. You will get the eigenspace to be s times some vector plus t times some other vector. Now, you've got 3 vectors here. 1, 2, and 3. 3 vectors that are eigenvectors. So these are 3 eigenvectors of the symmetric matrix A. So we have a basis of eigenvectors. Now we need to check whether we have an orthonormal basis or not. So if these 3 vectors belong to a set of orthonormal vectors, then yes, we have an orthonormal basis for eigenvectors. If not, then we need to translate them using some procedure. The procedure that we have learned in this class to make things orthonormal is the Gram-Schmidt procedure, where you are trying to project a vector onto the subspace and in the perpendicular subspace. So we are going to use Gram-Schmidt process here to make them into an orthonormal basis if they aren't. So first we need to check whether they are orthonormal or not. Well, a quick check tells you that the norm of these guys is not a 1. So you right away know that they are not orthonormal, but they still may be orthogonal. Let's try to check whether they are orthogonal or not. So if you have A as your symmetric matrix, you have the 3 eigenvectors that we found. We found the eigenvectors earlier, u1, u2, u3. These are all eigenvectors. So if they are eigenvectors, then they need to satisfy ax equal lambda x, right? So it should satisfy au equals 9u1, au2 equals 3u2, and au3 should equal 3u3, right? So this is essentially ax should equal lambda x. So you have 3 values of lambda, 9, 3, and 3. And you have 3 eigenvectors that correspond to that, u1, u2, u3. So because we have already found the eigenvectors, you can check this. They will satisfy these 3 criteria for the obtained u1, u2, u3 with the corresponding eigenvalues as 9, 3, and 3. Next, let us see if they are orthogonal or not. We already know that they are not orthonormal. Let us see if they are orthogonal or not. If you do u1, the dot product of u1 with u2, you will see that it is 0. So u1 is orthogonal to u2. And if you do u1 with u3, you will also see that it is 0. So u1 is orthogonal to u3. However, if you see the dot product of u2 and u3, that is in fact -2. It is not orthogonal. So u2 and u3 are not orthogonal with each other, which means that we are going to use Gram-Schmidt procedure to get an orthonormal basis. We still need to work on orthogonality between u2 and u3. Now, if the one thing that I want to point out is lambda equals 9 gave you that, lambda equals 3 gave you that, and lambda equals 3 gave you that. If the eigenvalues are different, then you right away get orthogonality. You got orthogonality here, and you got orthogonality here. It happened when the eigenvalues were different. But when you went for eigenvalues to be the same, u2 and u3 did not end up as orthogonal. That actually is a part of the theorem. If you have a symmetric matrix, then and u and v are eigenvectors with different eigenvalues, then u and v are orthogonal to each other. That symmetric matrix, actually in the homework problem, the hint was this, right? So if A is a symmetric matrix and u and v are eigenvectors, then this condition is true, where you have v transpose au equals u transpose av. So that is true if A is symmetric. And then you can use different eigenvalues, check whether u transpose v equals 0 or not. So, instead of saying A is symmetric, I simply stated this particular condition in the homework problem. But this is actually applicable for when A is symmetric. All right, so we are left with some work here. We have u1, we have u2, u3. We still need to work on orthogonality between u2 and u3. So we have the A as our symmetric matrix. u1, u2, u3 were obtained earlier as our 3 eigenvectors. u1 and u2 are orthogonal, u1 and u3 are orthogonal, but u2 and u3 are not orthogonal. And in this case, they have the same eigenvalue. So we are going to use the Gram-Schmidt procedure to find the orthogonal basis for the eigenspace lambda equals 3. So eigenspace lambda equals 3 covers these two cases. So for what is the Gram-Schmidt procedure? Initialize v1 to be u1, right? v1 is u1. We are only going for orthogonality between u2 and u3. So we are really applying the Gram-Schmidt procedure for u2 and u3. So when you start the process of Gram-Schmidt, the first step is what? Set the first vector to be the same as the first vector in your original basis. So we are setting v2 as u2. That's our first step of Gram-Schmidt procedure. v1 we don't even need to worry about because it was already orthogonal to u2 and u3. We're not even considering that. as a problem for our orthogonal basis. So this is your first step in Gram-Schmidt procedure. Next step is to find V3. How do you find V3? Well, remove the already projected vectors. So from U3, remove the projection of U3 on V1 minus the projection of U3 on V2. From U3, you get the orthogonal basis, the third vector in your orthogonal basis V3. So I'm simply running the Gram-Schmidt procedure over here. Project, remove it, project, remove it. I already have U1, U2, U3. I already have V1 and V2. I can use all of those guys over here to find my V3. V3 will be your third vector that will form the orthonormal basis. Actually, orthogonal basis. I still need to normalize it. So you have got V1 as U1, V2, first step of Gram-Schmidt procedure, set it as U2. And the last one is V3, which I found using subtracting the projections made on V1 and V2. So I found V3, an orthogonal version of U3. A version of U3 that is orthogonal to U2. So I've got these three as my orthogonal basis of eigenvectors. Just need to normalize it. So in order to normalize it, what do? We just divide each of those vectors by the norm, right? So we have, earlier we had 1, 2, -1, right? 1, 2, -1. We just divided by square root 6, the norm of that particular vector. Similarly, we did that for the second and the third column here, or V2 and V3. So we simply did V1 divided by the norm of V1, and then V2 divided by the norm of V2, and then V3 divided by the norm of V3. And we got an orthonormal basis for the eigenvectors of a symmetric matrix A. So Q here is a orthogonal matrix which has 3 columns. Each of these columns are orthonormal basis of the eigenvectors. And we can verify whether Q is orthogonal or not by checking for this. Q transpose Q, is it equal to identity or not? In other words, check Q transpose is I or not. Also, you can verify, because Q is orthogonal, whether it will diagonalize A or not. So if you look at the product Q transpose AQ with A as this and Q as this, it will diagonalize the matrix A, and all the entries in the diagonal will simply be what? 9, 3, and 3, right? So this will actually equal a 3 by 3 matrix in which you have 9, 3, and 3. Everything else will be a 0. And you can verify that. Next, the last thing really that we are going to look at is spectral decomposition. So how can you decompose a matrix A into vectors that are orthogonal? So that's called spectral decomposition. You can take any symmetric matrix A and you can decompose it as a sum of these products. So here you have A Q1 transpose plus lambda 2 Q2 transpose plus lambda n Qn transpose, where lambda 1, lambda 2, lambda n, these are all eigenvalues of matrix A. Q1, Q2, Q3, and so on up to Qn are forming the orthonormal basis for R to the n. These are all eigenvectors of A. So you can decompose any matrix as this. So in our earlier example, this is called spectral decomposition or eigen decomposition. In our earlier example, what that means is, if I go back, right? So this is, so if you look at what is Q1 over here, this was my Q1, Q2, Q3, right? So Q1, this was my Q3, and this was my Q2. These were columns of my orthogonal matrix Q. So if you did, my claim is this: if you did lambda 1 is what? 9 times Q1 transpose plus 3 times Q2 transpose plus 3 times Q3 transpose, you will get your original matrix A back. So you can decompose this symmetric matrix into pieces that are orthogonal vectors. So, and you need to scale them by their appropriate eigenvalues. So a symmetric matrix can be decomposed using this. And QJ transpose or QI transpose, this is the outer product as opposed to being the dot product. When you compute the dot product, you get one scalar value. When you take the outer product, which is this, you're actually getting an n by n matrix, right? So A is n by n, lambdas are your scalars, and Q1 transpose, Q2 transpose, these are all n by n matrices that are obtained by evaluating the outer product of QJ transpose. Now, spectral decomposition is actually equivalent to this. A equals Q D Q transpose. How are we getting this? Well, what was orthogonally diagonalizing a matrix? You were doing this, right? Q transpose A Q equals D. We are doing this. Now, if you multiply with Q here, Q inverse here, or Q transpose here, what do you have? You need to multiply here with Q transpose. Now, this goes away. What you're left with is A equals Q D Q transpose. So the matrix A can be decomposed as a product of three things. One is Q, the orthonormal, the orthonormal basis, right? Orthogonal matrix which has vectors as which has vectors which are orthonormal basis of the eigenvectors of A. D is your diagonal matrix with eigenvalues of A, and then you have the Q transpose, the transpose of the orthogonal matrix. So A can be decomposed as those three products. We can write this as this. So I can say this is A equals, we have Q1, Q2, Qn, right? These are all column vectors here. You are multiplying this with lambda 1, lambda 2, so on up to lambda n. And your another multiplication over there is Q1, Q2, Qn. These are all transposed. So if you carry out the multiplication here, here, and here, you will get back the square matrix, symmetric square matrix A. All right, this is all I have for you guys for today. I'm going to stop recording now. I think we can stop recording somewhere here. Stop recording.